Well, hello everybody. This is the second lecture of the first week, and today we're going to start on probability theory, which is to say what we're calling chapter 2 of the notes. And basically, probability theory starts off with set theory, and that means that we have to define a bunch of things. So we first of all define an experiment. This is a process which generates random data. And what that means is basically there's many things in this life that are random. And for example, wind speed. That's a process that generates random data. There is just what is the wind speed at any instant in time. Of course, that changes from instant to instant. And because we don't know ahead of time what it's going to be, we call that a random process. And the actual measurement of wind speed is an experiment. We're going to define a sample space. We're going to use capital S to denote that. It is an event. It's a set of all possible outcomes of an experiment. So the wind speed is all possible numbers between 0 and potentially infinity. An outcome is an individual result from the experiment, and basically an outcome is a realization of the experiment. So if I go outside and measure the wind speed right now and it's 22.6 kilometers per hour, that is a realization of this random process of wind speeds. An event is a collection of one or more of the possible outcomes, and of course this is a subset of the sample space. So we're going to use capital letters to denote events, so A, B, and so on and so forth. So the event A could be, for example, that the wind speed at any instant in time is between 20 and 30 kilometers an hour. So that's a subset of the sample space. A really useful way of depicting set theory is through Venn diagrams. And this is basically a graphical representation of the sample space and the events of interest. So, for example, we could have a Venn diagram of wind speeds. And basically, for Venn diagram, I just draw a box. And inside that box is all possible outcomes. Okay, so if there were wind speeds, then it's all possible outcomes from 0 to infinity. And I can say, okay, well, there's some subset of this, which I'll call event A, and this is the possibility that wind speeds, for example, are between 20 and 30 kilometers an hour. And we can have other subsets or events, and these may be overlapping. So if A is the wind speeds between 20 and 30 kilometers an hour, and B is wind speeds between 28 and 40 kilometers an hour, there is some overlap there. 28 to 30 is common between the two subsets, or the two events. And I think of this, of the Venn diagram as being a dartboard. I throw my dart randomly, and where it ends up is what event takes place. So if it ends up here, then neither A or B took place. If it happened to end up here, then event A took place. If it ended up here, then both event A and B took place. Okay, so I already mentioned subsets. So these events are subsets of the sample space. But more generally, we can say the event A is a subset of B if every outcome in A is also contained in B. And I show this using this notation here. It's sort of like a less than sign, but it's more like a sideways U. So A is subset of B if all of the values of A are also in B. So the picture of a Venn diagram of that event is shown here on the left-hand side. We can define the null set and we're going to use a 0 with a slash through it. So the null event is the impossible event. And this has 0 probability, so it's a point on the sample space with 0 area. My dart can never hit it. An example of this is a set of wind speeds that are both greater than 50 kilometers an hour and less than 10 kilometers an hour. You can't be both greater than 50 and less than 10 at the same time, so this is the impossible event, which is the null set. Once we define these events or subsets, we can define some operations on these subsets. First one is union. And we say A union B is the event that A occurs or B occurs. So this union basically means the word or. But it's an inclusive or. In the English language, or is usually exclusive. So if you say Mary or Jane went to the party, it usually means one of them went to the party, but not one of them went to the party, but not both. In probability theory, or means one or the other or both. Okay, so this union means A occurred or B occurred or both occurred. And you can see the picture of this on the right-hand side. Basically, the A union B is all of the area inside of A or B. And A union B, of course, is the same as B union A. And more generally speaking, the union of n events can be written as sort of like a summation, except it's a union, I equals 1 to n of the AIs. So that's a union. The next set operator that we'll consider is intersections, and we write this as A, and this is an upside down U. That means intersected B with B, and this event basically means the word and this corresponds to the English usage of the word and. If A intersection means the event that A occurred and B occurred at the same time. And it's shown over here on the right-hand side Venn diagram as the space that is contained in both A and B. And of course, A intersection B is the same as B intersection A. Some other properties is that the intersection of A with the sample space is just A itself. The intersection of A with itself is also A. So that's intersections. Another word we're going to see quite a bit of in the months to come is the word disjoint. This is the same as mutually exclusive. Let me just make a note of that. Oops, sorry. Disjoint equals mutually exclusive. The words mutually exclusive is actually a little bit more clear, but disjoint means that if one occurs, the other cannot occur, which is the same as mutually exclusive. And in terms of the Venn diagram, disjoint events A and B are events that have no overlap. So we can see that here in this Venn diagram. A and B have no overlap, so if the dart ends up in A, it cannot also be in B. Okay, or if it ends up in B, it cannot also be in A. So that's usually the way I test to see whether events are mutually exclusive or disjoint, is I ask myself the question, if one of them occurs, can the other also occur? If the answer to that is yes, then those circles must overlap. Okay, so they're not disjoint. If the answer is no, if one of them occurs, the other cannot occur, then they are disjoint or mutually exclusive. And if they are disjoint, the intersection between them is just equal to the null set. Another operator is the complement, and I'm going to write this as a little superscript C. You'll see complements written in various textbooks in quite a number of different ways. Sometimes a bar over the top of the event, sometimes it's a star, but we're going to use a C here. Basically, the complement of A is everything outside of A. So A, it could be this region here in the sample space. A complement then is everything outside of it. We can see automatically that there's some results to this. The union between A and its complement must just equal the total sample space. The intersection between A and its complement is the null set. In other words, you can't both be in A and not in A at the same time. The complement of A complement is just A again. And the complement of the sample space is the null set, or the impossible event. In other words, sample space contains all possible events, so its complement has to be the impossible event. There's some laws that come out of these set operations. De Morgan's laws basically say that the complement of a union is the intersection of the complements. And we can see that here to some extent. The union is everything shown in red, and the complement of that is everything outside of it. If I look at it in terms of the complement, the intersection of the complements, the A complement is everything in green, and B complement is everything in red. The intersection between them is where we have both red and green. And that's everything outside of A or B. So I mentioned complement of union is the intersection of the complements. Complement of an intersection is the union of the complements. So A intersection B complement is A complement union B complement. And again, we can show that using Venn diagram. So the complement of the intersection is everything except the intersection. So all the red stuff here. And if I look at A complement is everything outside of A, and B complement is everything outside of B. So the union is everything that has red or green in it, or red or both. And the only place that doesn't is this point, this space, the intersection here. So that basically is the same as what we have over here. Okay, I mentioned disjoint events. These are events that are mutually exclusive. The test is if one occurs, the other cannot. So that's the question you ask yourself. If events A and B are disjoint, then our Venn diagram looks like this, and the intersection between them is the null or the impossible event. Another thing that we'll deal with are so-called collectively exhaustive events. This is a set of events that span or cover the entire sample space. Usually we consider these events to be disjoint, but they don't have to be necessarily. When we come to total probability theorem, we're going to assume that they are disjoint, and in fact they have to be. So basically A1, A2, A3, A4, A5 span the entire sample set, then these A's are collectively exhaustive. In other words, the union between them is equal to the sample space. So let's illustrate these concepts with some examples. Example 2.1 is a sample space example. Suppose that we toss a coin twice and we want to list the possible outcomes. One possible result of this experiment is to list the number of heads which turn up. Our sample space in this case is, if we flip a coin twice, we could end up with no heads, or we could end up with one head, or we could end up with two heads. So basically our sample space consists of 0 heads, 1 head, or 2 heads. And we can ask various questions about this experiment. For example, what is the probability that less than 2 heads show up? Our event of interest is A equals 0, 1. So if 0 heads show up or 1 head show up, that's less than 2 heads. And this is a subset of S. And the question is, how many possible subsets of A are there? Let's just draw a little picture here. Our sample space is going to look like, this. And this is what we call S. And it basically is divided into 3 regions that look something like this. Okay, so again, if I throw my dart and it lands in the region denoted by 2, it means I got 2 heads show up. And my actual samples are, I guess if we start with this, tail, 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 head, head, tail, and head, head. Okay, but our sample space here is just the number of heads that turned up. So the actual details there just lead to these numbers that we're interested in. This event A is going to be, let me try that again, is going to look like this. It's a subset of our sample space S. We've got this is 1, this is another, so 0, 1, 2, and my event A then, is this space here. And so that's A. Okay. So the last question is, how many possible subsets of A are there? Well, I guess we can just enumerate them. We've got one is 0, another is 1, another is 2, and then we've got 0, 1, 0, 2, that's it, 0, 1, 0, 2, then we've got 1, 2, and then of course we got all 3. And I think we can put in the null set is, I suppose, theoretically a subset, although it's an impossible subset, so I normally don't throw that in. Okay, so those are the possible subsets, and if we exclude this one, we got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So the answer to this question is 7. I think I got them all. Anybody think of anything else? 0, 1, 0, 2, 0, 1, 2. Yep, that's it. Okay. So the other way of doing this experiment is to record the sequence of heads and tails in our sample space. And this is actually more complete information. Our sample space now looks like this. And we've got actually 4 spaces here. And one of them is tail, tail. One of them is tail, head. One of them is head, tail. And one of them is head, head. Okay. And basically, if we know this, we can recover the information in this sample space up here, because we can figure out what whether if we land in tail tail, we know that the number of heads was 0. I should also point out that the sample space, the areas of the spaces in the sample space is related to the probability of them occurring, which is to say the bigger the area, the more likely my dart is going to land in it. And we know that if this is a fair coin, the probability of getting tail tail is the same as getting tail and a head, and which is the same as getting a head then a tail, and same as head head. So these are all probably 1/4. But the probability of getting 0 heads is just the probability of falling in here. So this area here for 0 is 1/4. But the probability of getting 2 heads is 2 areas. And so this one in the middle has a bigger area than the 0 or 2. 2 heads is probability 1/4. Now I can sort of illustrate this as shown here. The event that we get 0 head showing up corresponds to the event that tail tail took place. But the event that 1 head shows up corresponds to that we got tail head or head tail. So there's an or there, that's a union. And so basically the probability of this happening is the probability of this happening plus the probability of this happening. And the probability of 2 heads must correspond to just HH. Okay, so let's illustrate some of this with an example. An engineering construction firm is currently working on power plants at 3 different sites. Let's let AI denote the event that the plant at site A is completed by the contract date, so on time. Using only set theoretic language, only the AIs, intersections, unions, and complements describe each of the following events. In each case, also draw a Venn diagram and shade the region corresponding to the event. At least one plant is completed by the contract date. Well, we know if at least one plant is completed by the contract date, then either A1 or A2 or A3 took place. The word there is or, so we know that this is a union. So we can actually write this out. At least one plant completed on time is A1 union, A2 union, A3. And of course the union then is the area enclosed by all 3 of them, shown in blue here. What's the next one? All plants are completed by the contract date. Well, now we have to have all 3 of them completed on time. So it's got to be A1 and A2 and A3 if AI is the event that it's completed on time. So and there means intersection. So we write this as A1 intersection A2 intersection A3. And in our Venn diagram, the location where all 3 of them take place is the intersection between all 3 circles. What's the next one? Exactly one plant is completed by the contract date. So this is a little bit more difficult. It means either only A1 or only A2 or only A3. And there's an or there, so it's a union, but we've got to figure out how do we do the only A1 part. Well, let's take a look at that. We know only A1 is going to be this region here. So it's the part of A1 that's outside of A2 and outside of A3. So we could say, okay, that part is A1 intersection the complement of A2 intersection the complement of A3, and this thing corresponds to this region here. But we could also be here. If we're in this part here, then only A2 has taken place, and that's written as A2 intersected with A1 complement intersection with A3 complement, or we could be here. So the ors turn into unions, and then this last one is the event that A3 occurs but A1 doesn't occur and A2 doesn't occur. So then we can ask usually when we're doing this, we're trying to compute probabilities, and anytime I see unions, the first thing I ask myself is if these things are disjoint. And if they're disjoint, it means if I'm in this space, I cannot be in the other two spaces. In other words, if I'm here, can I be here or here? No, it can't be. So that means these three spaces are disjoint. And that concludes first part of lecture number 2. And I'll be continuing shortly with the second part.